Hello. So we had this actually, the session was in the past week. Somehow I couldn't record the session, so I'm recording it again. I will again go through the same slides which we had discussed, same questions, and everything is written in the slides which we had discussed in the past week. So we will go through it again, and I will upload the session. Let me first confirm whether it is recording or not. So we first discussed this question on KCL and KVL, and we discussed what is KCL and what is KVL. That is, KCL is a current law, which says that if the current comes in at the node and the currents are leaving it from the node, they have to be equal. So here I will use red color. So here you see that I1, I2, and I3 are coming in and no current is leaving. So I1 plus I2 plus I3 will be equivalent to 0. And we studied that this is due to conservation of charge. Because if for the same amount of time, see this equation, Q1, Q2, and Q3 charges are flowing from three terminals for the same amount of time. So we see that Q1 plus Q2 plus Q3 have to be equal to 0 from the conservation of charge, because charge can either be created or destroyed. So this was about KCL. Now, if we look at KVL, what does KVL say? In a system, total energy is conserved. And we know energy is Q times V in this equation. So that means if there is a potential here, that is V naught, and there are two resistors here, let's say, and they have drops V1, V2. So increasing if we go from this node, take this node A, if we traverse this path, so there is an increase in potential, that is V0. And now I have an equivalent sign. Now I have to write it on the right hand side. So it has to be equivalent to the drops. So signs will be positive on the right hand side. So this is V1, drop in potential, plus V2. So this is from the conservation of energy. Next, we went to solve this question based on two methods, that KCL and KVL. And we'll solve the equations. I will just directly go through them. If now I write a KCL at node V1, writing it KCL at here, I have three current components, right? One between V1 and 15 volt through 2 kilo ohm, and another is V1 to V2 through 14 kilo ohm, and another is between V1 and V3 to 3 kilo ohm. That's what is written here. V1 minus 15 by 2K plus V1 minus V2 by 14K and plus V1 minus V3 by 3K. This is simple. V is equal to IR, Ohm's law, like written here, V1 minus V2 by R. Okay. Simply, this is again simplified, and we get equation number 1 of the format A1x plus B1y plus C1z is equivalent to P1. We'll see how we will use this equation. This is of this format. Again, now at node V2. Node V2 is this one. See the components. Current going here through 2 kilo ohm, and current going here between V2 and 1 volt to 2 kilo ohm. Similarly, writing it, V2 minus V1 by 14K, V2 minus V1 by 2K, and V2 minus V3 by 2K. On simplifying, we get minus V1 plus 15V2 minus 7V3 is equivalent to 7. So again, this is of the format of P2X plus B2Y plus C2Z equivalent to P2, right? So now we need three equations to solve three variables, right? So we can write third equation for node V3. Again, look, what are the current components? Between V3 and 1 volt to 2 kilo ohm, V3 and V2 to 2 kilo ohm, and V3 and V1 to 3 kilo ohm. So it will be written here V3 minus 1 by 2K plus V3 minus V2 by 2K and V3 minus V1 by 3K. Let's again cross check the recording. Slightly afraid because last time there was some issue and now I have to record again. So on simplifying, we get third equation again of the format A3x plus B3y plus C3z equivalent to C3. So these are the three equations. Now let's stop here. How can you solve these equations? There are simple methods, right? Substitution method. Like we discussed, if you have ax plus by is equivalent to c, a1, b1, c1, and a2x plus b2y equivalent to c2. Equation number 1, equation number 2. What you will do is, from the first equation, you will see x is, from first term, x is c1 minus b1y by a1. And now you substitute in 2. I will get a2 by a1 c1 minus b1y plus b2y equal to c2. Now you can get y from this equation because this is now in single variable. This is for substitution method. Okay, so we will discuss after we write the KVL. Okay, so now if we want to solve this question through KVL, we can do that, right? So we need three loops. So I have drawn here loop 1, loop 2, and loop 3. And I'm assuming a current of I1 in the upper loop, third loop, and I2 in the first loop, and I3 in the second loop. Now I need to write a KVL for, let's say, loop 1. So what I will do, I will traverse a path given by this direction. First is increase in potential, that is 15 volt. And then in the resistor, there is a drop in potential, right? So that, and the current flowing is I2. So it will be 15 minus I2 times 2K. This is 2 kilo ohm. And then see here in the 14K, resistor, what is the current flowing due to this loop? I2. And what is the current flowing here? In this loop, this is I1, right? So this will be I2 plus I1. That's why the drop is minus 14K, I1 plus I2, right? And then we go through this loop, this resistor. And this has a drop of 2 kilo ohm. And what is the current? I2. And I3 is flowing in the opposite direction. So it will be minus I3. So 2K, I2 minus I3. And then drop in potential of 1 volt, so minus 1 volt equal to 0. Now, let's say this is for loop 1. Let's say for loop 2. Let us traverse the path from here. So this will be 1 volt minus 2 kilo ohm What is the current flowing through it? This is I3 minus I2, right? Then, so this is a 2 kilo ohm between V2 and V3. I have a drop of 2 kilo ohm, and the current flowing is I3 plus I1, and then again for 2 kilo ohm between V3 node and 1 node. So this will be minus times 2K I3 and minus 1 volt equal to 0, 1 and 1 will go. It will be simply 2K times I1 minus times 2K times I2, 6 times 6K times I2. So this will be equation number 2. Similarly, you can write equation number 3 by using the loop 3 and then solve the equations. Okay. So now I will discuss one method which we can use to solve this set of linear equations. Once. Okay, wait, you can use the substitution method, but let's discuss another method that is Cramer's rule. So now, if you have three equations, which I had written down in the previous slides, that is a1x plus b1y plus c1z equal to p1, and a2x plus b2y plus c2z equal to p2, and third equation is a3x plus b3y plus c3z is equivalent to p3. Now, what are the steps? First, find the determinant delta of the system, that is a1, a2, a3, b1, b2, b3, and c1, c2, c3. If you find this, then write delta 1, delta 2, delta 3. And how do you find delta 1, delta 2, delta 3? You just replace that column by the right hand side constants, these p1, p2, p3. Delta 1, replace the first column, delta 2, replace the second column, and delta 3, replace the third column. And by doing so, now you can get x1, that is given by delta 1 by delta, y, delta 2 by delta, and z, delta 3 by delta. So this is the easiest one, which can give you answers very quickly. So you can use this method to solve your set of linear equations. Alright. So now let's say we are clear about this, and now we can move to next part. So the question is find the DC voltage at the output node. So this is the output node which is written here. We have to find the DC voltage. So as we had discussed in the session, that for the DC, the capacitor blocks, and for the AC, after a particular frequency, it can act as a short. Right? The question says, assuming the capacitor is shorted for the input frequency signal, calculate the amplitude of the output signal. So this is the second part. First, we'll find the DC voltage. So here it's written capacitor DC, it blocks, open circuit, and AC, it feeds, that is short circuit. So what does it mean feeds? Feeds means it allows the signal to pass. So now for the DC, capacitor is blocked, we will get this equivalent circuit. Now it's easy to find V0 because this is simple voltage divider. So we need to find the voltage across 100 ohm. This is 100 ohm, right? 50 plus 50. So this is 100 divided by 500 plus 100. This is 12 by 6. That is 2 volt. So this is DC voltage. Now part 2 is AC. Now the question said that for the frequency, input frequency, the capacitor is short. So that's why I shorted here. So we can get the circuit here like this, and we have in the parallel also there is a capacitor, so it will also act as a short. So it will bypass the 50 ohm resistor. So that's why there is only 50 ohm. And then previously you saw there was a 100 ohm. So this is the equivalent circuit. Now we need to find V out. So V out total will be VDC plus VAC. Now in this part we only need to find VAC. So that's why we will use only AC signal, and the DC will go to ground or short. So this is the equivalent circuit. This is V in 50 ohm and 550 ohm are in parallel. You will get this is equivalent to here R dash, and now the small signal output voltage will be again given by voltage divider between R dash and 50 ohm written here. So this is V out dot by R dash, this is R dash plus 50 multiplied by V in. So that is 5, comes out to be 500 divided by 500 plus 550, and it comes out to be 38.9. This is this first type of questions is solved by using superposition principle. You can get the response from the system using either source at one time. All right. So you can go check the network analysis you may have studied in your first, second years of the BTech. Okay, then since the week was on the diode, so we can have a small 1 second. Give me 1 second. So the discussion is on the diode. First, let's see the diode. And we had a discussion that this is how the diode is. This is P side, this is N side, this is P side, this is N side. And you have a holes here on the P side, and you have the electron here on the N side. And in between, you have a space charge, where positive is on the N side and negative is on the P side. So we had discussed about some band diagrams. Let's say this is a material which has a band diagram like this, and what happens is these Fermi levels they want to match. So what happens is electron transfer occurs from a Fermi level at higher energy to the Fermi level at lower energy. So we get a equilibrium state. So here, this is how the band diagram looks after the transfer of electrons, and the EF you see here is uniform throughout the structure. So what is this energy difference? This is your VBI, and VBI is your built-in potential, which is potential due to the region you saw here. Alright, there's something we have discussed. Okay, so what happens in forward bias? In forward bias, we discussed that when you apply a positive potential to a system, its energy go down, and when you apply a negative supply, like here, these bands will go up, and you apply positive, these bands will go down. So, equivalently, we can say that this potential difference QVBI it decreases, right? So it may now be lesser. Okay. So that is what happens in the forward bias, and the reverse bias reverse occurs because we have positive potential here and negative here. So there is an increase in potential. So here one student may ask the question about what will happen to the Fermi level if we apply the bias. So I had made this diagram that is of a simple bar and type bar, and it has a equilibrium energy band diagram like this. Now if I apply positive here, negative here, so what will happen is the bands will bend in this way. And this is Fermi level, this is EC, and this is EV. This is how the bands will bend, and there will be a current transmit. So here actually is I have shown how bands will go up and bands will go down. So this is VBI plus VA. That is sorry. This should be VBI minus VA if I apply the forward bias, and this is VBI plus VA if we apply a reverse bias. Increase in potential, right? Forward bias. This is plus. So now the question was about the diode. Wait, let me check. Okay. And another thing is for the diode, it turns on after a certain voltage, which you call as knee voltage, or in MOSFETs, treat it as threshold voltage. So, but here for this question, we are saying that the diode is completely ideal. That means once you apply a positive voltage, it conducts, and once you apply a negative voltage, it does not conduct. So I have two diodes here, D1 and D2, and V1 is applied. So when it is positive, D1 is conducting, and V out will raise V in, right? And when you apply negative voltage, so D1 turns off and D2 is on for the negative. So again follows the V in. Again follows the V in. So this is how the plot will act. This is V out. If we were, it does just directly follows the V in. Y is equal to X. So D1 is on for V in positive, D2 is on for V in negative. Right? Okay. Another question is find the voltage across the diode. What is the answer after third rotation? I naught is 10 raised to the power minus 13 amps. I naught is called as the reverse saturation current. Yes. Non-ideality factor 1 and thermal equivalent voltage of this. Thermal equivalent voltages. Okay, I understand this. So this is how the direct current equation is geared. ID is equal to I naught exponential of ED by NVT minus 1. And thermal voltages, KT by Q. K is voltage constant, T is temperature, Q is charge. So what we assume here is that the diode is on and Vd is sufficient enough such that exponential of Vd by nVt is greater than 1 and neta is 1, so we can ignore this. So we'll get Id by I naught is equivalent to exponential of Vd by n is 1 d. Okay, so step 1, we assume that the diode voltage is 0. So we get from Ohm's law, if I assume V naught is 0, ID is 4 minus V naught by 1k, right? So if V naught is 0, ID is simply 4 by 1k. That is 4 milliampere. So that's what is written in step 1. So now from this, if I just rewrite this equation, V naught is equivalent to Vt ln of ID by I naught. So that is written here as equation third. Vd is Kt ln of ID by I naught. So Vd or V naught is 0.025 ln of 4 milliampere by 10 is power minus 13. To solve this, you will get a V naught of 610.304 millivolts. Okay, okay. Now step 2, again, we will use ID is equivalent to 4 minus Vd by 1k. And now Vd is 610.304 millivolts. So ID is 3.3897 milliampere. This is from the step second. And now again you calculate Vd from the step. You will get 606.16 millivolt. Again, step 3, repeat. ID is 4 minus 606.16 millivolt by 1k, you will get 3.39. And now you calculate V naught, which comes out to be 606 millivolt or 6.606 volt. So this is how you do it using a iteration method. Okay, the question is find the DC current ID1 equal to ID2 equal to ID using piecewise linear model with cut-in voltage of 0.7. Assume non-ideality of 1 and thermal voltage of 0.025. Find the DC output voltage. Find the minimum input signal frequency. Such that output voltage. Okay. First, piecewise linear model. You see from this figure, ID versus VD. You have this cut-in voltage of V down. So from piecewise linear model, we can just do this. I is V minus V gamma by R on. This is the model, or you can just replace it by V gamma. This is R on. Okay, this is a piecewise linear model for diode, and the ideal factor is 1. So we had discussed that it depends on multiple nonlinearities, how the current is flowing, which process is dominant in which region. So it has been seen the eta is in range of 1 to 2. Okay, so this is again the piecewise linear model. Okay, so now let's see how we can draw the equivalent circuit. So DC circuit is simple. This is 6 kilo ohm and D1 and D2 in this direction. And we treat it as a real diodes. So this is zero point 0.7 volt is given as cut-in voltage, and we can draw it as zero point 0.7, and this is RD and RD. Okay. So if we have to find V naught, so I can directly write the. So first let me find the DC voltage. Okay. So I can just write here 12 volt minus I times 6 kilo ohm minus zero point 0.7 minus zero point 0.7 minus 2 times IRD equivalent to 0. And from the equation here, I can write RD as di by dV I naught exponential of VT by VT on 1 by VT, and this is approximately equivalent to I. So RD comes out to be VT by RD. So I substitute it here, so I get 2 times VT, right? Then if I directly see here between these nodes, can I directly write? Now I have the potential here across this resistor, that is 2 VT, and this is 2 VT total, and this is points and points. So I can directly write the V. I don't need to calculate I to calculate V naught. That is equivalent to 1.4 plus 0.05. This is 1.45 volt. Here, I have written it here. So now you find them. Okay, I can just directly write the ID as well. You can just calculate it from here. This is 12 minus 1.2. Sorry, 12 minus 1.4 minus 2 times this is 0.5, 1.5, and you can just also calculate the ID as well. All right. So it comes up to be fine. Now part two. Part two is AC part, and but we have to find the input signal frequency such that the output voltage is at 50 millivolt. First, we will draw the equivalent circuit. This is capacitor, 6 kilo ohm resistor, RD1 plus RD2. This is VT by ID. RD1 is equivalent to RD2 is equal to 13.95 ohm. And this is V input. So now Okay. If you have a circuit like this, you can directly write V naught is equivalent to R1 divided by R1 plus R2 multiply V in. Excellent. But you have two resistors in parallel, and then it is in series with capacitance and the 50 ohm. First, let's find the R dash, which is the resistance looking into this parallel combination. So this will be RD1 plus RD2 multiply R divided by R plus RD1 plus RD2. So R dash comes out to be 27.77. Then we have XC, that is the reactance of the capacitance. So we can write V output as R dash divided by R dash plus 51 plus 1 by j omega C. Impedance is 1 plus A, 1 plus, sorry, A plus iota B. A is the real part is only the resistive part, and imaginary part is the reactive part, which can be capacitive or inductive. So magnitude is total magnitude or impedance is given by square root of A square plus B square. So now I will take the magnitude. So this is 50 millivolt. We need to find the frequency, and the output is at 50 millivolt. So that's why here this is 50 millivolt is equivalent to magnitude R dash divided by magnitude R dash plus 50 plus 1 by j omega C. So this is equivalent multiplied by 200 millivolt. Milli and milli will go. And you see that in the equations you will have this omega squared. You know the C. Now only unknown is omega, so you can find this omega as 12.6 kiloradian per second. So this is what we discussed in the sessions. I had missed the recording. So I will upload this recording. This is for the lesson time, obviously, because there was any interaction. So I guess that's it. So I will see you in the next session.